In this video series, we are going to look at how neurons generate, propagate, and pass action potentials. While we are specifically going to focus on neurons, this information is relatable to any cell in the human body that has the capacity to generate action potentials. Perhaps most importantly, from an academic standpoint, I'm going to teach you how to interpret this graph, which mystifies countless people. When discussing how neurons generate action potentials and then ultimately propagate and pass them, the first thing that is necessary to comprehend are what are called the synapses that exist between two neurons. So in this image, we have what we'll call neuron number 1, oftentimes referred to as the presynaptic neuron, and we have neuron number 2, oftentimes called the postsynaptic neuron. Where these two neurons meet is known as the synapses that exist between them. Now, the synapses are going to be between, usually, the axon terminal buttons of neuron number 1, or the presynaptic neuron, and the dendrites of neuron number 2, or the postsynaptic neuron. Now what we're going to do is focus in on one of those synapses. As a reminder from anatomy, the axon terminal buttons, or boutons, that can be said either way depending upon the spelling, they make up the very ends of the axon terminals. Specifically, where the axon terminals swell at the very end, those swellings are referred to as the axon terminal buttons. The axon terminal buttons make up the first parts of the synapses. And in our case, these axon terminal buttons are part of neuron number 1, or the presynaptic neuron. When looking at neuron number 2, or the postsynaptic neuron, the portion of the dendrites, or the portion of the cell body, either one, the portion of the dendrites or the portion of the cell body, that lies right underneath and next to where the axon terminal buttons are, that is going to be the last part, or the end, of the synapses. So as I said, what we are going to do is only look at one synapse, right, where one axon terminal button from a presynaptic neuron meets a portion of the dendrite of a postsynaptic neuron. And we're going to look at that one synapse more thoroughly and discuss what happens there. So this image is a close-up of one synapse. What you see in the image is one axon terminal button of a presynaptic neuron from the prior image, that would have been neuron number 1, meeting the dendrite, or possibly the cell body, of another neuron. That would have been neuron number 2, or the postsynaptic neuron from the prior image. Where this axon terminal button is meeting this dendrite is referred to as a synapse. This is a synapse between two neurons. I must say that synapses do not have to be between two neurons. You could have the axon terminal buttons of one neuron meeting another cell, which is not another neuron, and that would still be a synapse. But in this discussion, we are discussing neurons and how they generate action potential, so we are going to continue to look at the synapse between two neurons. In this case, when you have a synapse between two neurons, it's going to consist of the axon terminal button of the presynaptic neuron, or neuron number 1, and the dendrite or cell body of the postsynaptic neuron. Additionally, there's a space that actually exists between these two neurons, between the axon terminal button and the dendrite. That space that exists is referred to as the synaptic cleft. It is literally an empty space that exists between the pre- and postsynaptic neuron. Perhaps now the names make a little bit more sense to you as well. Why would we call neuron number 1 the presynaptic neuron? Well, it comes before the synapse. Why would we call neuron number 2 the postsynaptic neuron? Well, because it comes after the synapse. And mind you, while we're only looking at one synapse, in reality, there would most likely be thousands of these that would be formed between the two neurons. If we look inside of the axon terminal button of the presynaptic neuron, we are going to find all these spherical things called vesicles. And these vesicles, in this case, are going to be filled with chemical messengers called neurotransmitters. Now, what's ultimately going to happen is, because of the fact that the presynaptic neuron, neuron number 1, generates an action potential, which we will get to later on in the lecture, what's going to happen is those vesicles filled with neurotransmitters, these chemical messengers, will go to the distal end of the axon terminal button plasma membrane and then release these neurotransmitters through a process called exocytosis. And those neurotransmitters, as you see, are released into what? The synaptic cleft, the space that exists between the axon terminal button of the presynaptic neuron and the dendrite of the postsynaptic neuron. Now, these neurotransmitters, as I've said, are chemical messengers. So what they're going to do is pass a message to another cell. And I think rather obviously, we can look at this image and we can say, well, those neurotransmitters, those chemical messengers, are probably going to pass that information to the postsynaptic neuron, right? The second neuron that we've been discussing, neuron number 2. But how exactly do they do that? Well, if you look at the dendrite, the portion of the dendrite that is right underneath where the axon terminal button is, you'll find that there are receptors that exist on that dendrite. So let's take a closer look at that. So what we are looking at now is a close-up of one receptor within the plasma membrane of the dendrite of the postsynaptic neuron. As was depicted in the prior image, there would be many of these, but we are just focusing on one to try to understand how it works. Now, this would be the inside of the neuron, so the intracellular fluid or the cytosol. Out here would be where the synaptic cleft is located, right? And within that synaptic cleft, there would be fluid. It says extracellular fluid, but more appropriately, that would be referred to as the interstitial fluid. And you can see what's floating around in the interstitial fluid are these triangular shaped molecules. And for the moment, we can ignore acetylcholine or ACH there, and we will just say that those are the neurotransmitters floating around in the synaptic cleft, the fluid of the synaptic cleft. Now, this receptor is, for our discussions, going to be able to bind that neurotransmitter that has been released by the presynaptic neuron. This receptor has binding sites located on it, and they are specific binding sites for that specific neurotransmitter. If we move over to the right, we can actually see the neurotransmitters binding to that specific receptor. Now, these receptors have a specific name. They're called ligand-gated channels. Where do they get that name from? They get the name from the fact that a ligand has to bind to them to remove the fact that they're gated, right? By that, gated, it means that they're closed. Okay, so these are ligand-gated channels. They're gated channels, meaning that they're closed. And then when a ligand, which is just a chemical messenger, like a neurotransmitter, neurotransmitters are ligands, comes along and binds to that ligand-gated channel, then the gating will be removed, and all of a sudden, specific ions or other molecules would then be able to move through that specific receptor or channel. So let's go back to the prior image and try and get a bigger picture of what's happening here. Neurotransmitters, which are a type of ligand, have been released from the axon terminal button of the presynaptic neuron. These neurotransmitters are floating around in the synaptic cleft, and what they will ultimately do is bind to receptors located on the plasma membrane of the dendrite of the postsynaptic neuron. Now, these receptors, which are ligand-gated channels, will open up when these neurotransmitters bind to them. Now, what does them opening up actually result in? What these ligand-gated channels actually are ion channels. They are largely what are referred to as nonspecific cation channels, meaning most ions with a positive charge, when the channel opens up, can flow through them. As this lecture moves on now, what would be very helpful is if you understood in its entirety what the resting membrane potential is and how it develops. If you need assistance, I do have a video which covers the resting membrane potential. I am not going to go over that in this lecture, but it is somewhat of a necessary prerequisite to understand the next part of this. So you might consider going and watching that video before continuing on if you are not already familiar with the resting membrane potential. So let's try and draw this out and be more specific. Here we have an axon terminal and axon terminal button. Inside of this axon terminal button, we have vesicles filled with neurotransmitters. Right underneath this axon terminal button is going to be a dendrite, specifically a portion of one dendrite. And located on the portion of that one dendrite are going to be receptors, ligand-gated channels, for that specific neurotransmitter that is about to be released. So what's going to happen first is the presynaptic neuron, or neuron number 1, is going to generate an action potential. That action potential is going to cause exocytosis of these neurotransmitters into the synaptic cleft. Now that we've reached this point, I want to be a little bit more specific about the type of neurotransmitter that we're discussing. There are many, many different types of neurotransmitters, but we can assign this one somewhat of a broad category, which is going to be an excitatory neurotransmitter, because that is what's going to be used in order to allow this other neuron, the postsynaptic neuron, neuron number 2, to generate an action potential. Excitatory neurotransmitters are going to excite the other cell, and we'll get into more of what exactly excite means in a little bit. But I did want to assign some sort of name to this neurotransmitter now. So this excitatory neurotransmitter is going to bind to these ligand-gated channels. And when these excitatory neurotransmitters bind to these ligand-gated channels, it's going to cause these ligand-gated channels to open up. As I've said, these are non-specific cation channels. So ions with a positive charge can generally flow through them. This brings me, again, to the resting membrane potential. As I've said, you may want to consider watching that lecture before seeing this part. It would make much more sense. Anyways, inside of the postsynaptic neuron, the resting membrane potential is going to be approximately negative 70 millivolts. We know a couple things. Potassium is high inside of this neuron, and sodium is low. And on the outside, the opposite is true. Sodium concentrations are high, and potassium concentrations are low. All right, so if we open up these ligand-gated channels, and that allows any ion with a positive charge to flow through them, what's going to happen? Well, you may think, and you would be partly right, that potassium is going to want to flow through these channels because even though it has an electrical driving force pulling it back, it still has a stronger chemical driving force to leave because of the fact that inside of the neuron, we are not at potassium's equilibrium potential. So if we open up basically extra channels for potassium to leave through than it normally has, its normal leak channels that it has, it is going to want to leave, but it's not going to be able to leave at a very fast rate. Right? Yes, some potassium theoretically is going to leave, but in reality, the amount of potassium that's leaving is quite insignificant because of the fact that there's a very strong electrical driving force pulling potassium back, so its drive to leave is heavily reduced. Yes, it still has a chemical driving force to leave, meaning a diffusion gradient. It wants to go from the inside where it's high to the outside where it is low. That chemical driving force is stronger than the electrical driving force. The chemical driving force for it to leave is stronger than the electrical driving force pulling it back. So if you open up extra channels, potassium will leave. But you have to recognize that this very strong negative electrical driving force is pulling the potassium ions back significantly, and thus the rate at which potassium is really going to be able to leave through these channels and go to the outside, meaning follow its chemical driving force to the outside, is not all that great. Now, what is great is what's going to happen with regard to sodium. Sodium is another positively charged ion, so it can flow through these channels as well. And what do we know about sodium? Well, sodium certainly has a chemical driving force to want to enter, right? It's high on the outside, and it's low on the inside. So yeah, it wants to come in through a chemical driving force. But what also does it have? It has a very strong electrical driving force to enter. The inside is negative 70 millivolts. So not only does sodium have a chemical driving force to enter, but it has an electrical driving force to enter. Point being, if you open up channels in the membrane that sodium can travel through, lots of sodium is going to come into the cell. In this case, come into the neuron. Sodium has a very strong desire to enter into neurons and a lot of other cells because of this reason. Right? It has a very strong chemical and electrical driving force pulling it in, but there are not many leak channels for sodium to come in through, so it's just waiting to have other channels open up that will allow it to come in. And that's exactly what these excitatory neurotransmitters released by the presynaptic neuron, neuron number 1, are going to do. These excitatory neurotransmitters are going to cause these ligand-gated channels, which are, again, really basically non-specific cation channels, to open up. And what that's going to do is going to really allow for sodium to shoot into the postsynaptic neuron, specifically into this one dendritic region of the postsynaptic neuron. So what is sodium entering into this dendritic region of the postsynaptic neuron going to do exactly? So I'm not going to draw the presynaptic neuron again, but what's going to happen here is these excitatory neurotransmitters are again going to open up these ligand-gated channels, non-specific, or more academically correct, non-selective, means the same thing, cation channels. And when they open up, that's going to serve as a passageway for sodium to come in. So you can think, what do excitatory neurotransmitters really do to postsynaptic neurons? Oftentimes what they do is they increase their sodium permeability by essentially opening up sodium channels. Although they're not exclusively specific to sodium, that's really what's happening. And sodium is going to come in through both a strong chemical and electrical driving force, because the interior of this dendritic region of the neuron, the postsynaptic neuron, is negative 70 millivolts. And as sodium enters, the inside is going to be gaining sodium ions. And as the inside of this dendritic region gains sodium ions, of course the inside is going to become more positive, right? We call this a depolarization. As the inside gains positively charged sodium ions, the inside of the neuron is going to become more positive because it's gaining more positively charged ions. How much exactly it depolarizes or becomes more positive is, of course, impossible for us to determine under this specific circumstance. There's so many things that are going to influence how great of a depolarization is going to happen at this specific dendritic region. Let's just say that it depolarizes by 30 millivolts. I don't know, I'm just making things up for the sake of simplicity. Let's say that it goes from negative 70 millivolts to negative 40 millivolts. Okay? The influx of sodium ions has depolarized this dendritic region by 30 millivolts. And now we need to talk about something that is oftentimes not addressed in the appropriate way that it should be. When it is said that a neuron has a resting membrane potential around negative 70 millivolts, that means every portion of that neuron has a resting membrane potential of around negative 70 millivolts. The resting membrane potential will extend all throughout the dendritic regions, into the cell body, into the axon hillock, into the initial segment, all the way down the axon and into the axon terminals and down into the buttons. Every single one of these regions has a resting membrane potential of around negative 70 millivolts. And the really important thing here is, just because you depolarize one of these regions does not mean anything happens to the other regions. I mean, it's going to influence them ultimately in some ways, perhaps, as we'll see. But the point I'm making is, just because we depolarize this one dendritic region from negative 70 to negative 40 millivolts right here, that does not mean anything has happened inside, for example, of the axon hillock just yet. Inside of the axon hillock, it would still be negative 70 as it always is. All we've done so far in our discussion is we have depolarized one portion of one dendrite on the postsynaptic, that is part of the postsynaptic neuron. Excitatory neurotransmitters were released onto that one specific portion of that one dendrite, and that allowed then for some sodium to come in and depolarize that one specific region. It is fundamental that you understand that fact in order to be able to understand everything else about what's going to occur with regard to the action potential. The next thing that's very important to understand is there's not just going to be one synapse between a pre- and postsynaptic neuron. There, in reality, is going to be thousands of synapses. These textbook images simplify these images intentionally, and they should. But if this were real, there would be thousands of axon terminals and axon terminal buttons, and there would be thousands of different dendritic extensions. And that's to drive home the point that in reality, when this presynaptic neuron generates an action potential and it releases excitatory neurotransmitters, it's releasing those excitatory neurotransmitters through thousands of synapses. And what that also really means is that sodium is going to be entering into thousands of different dendritic regions within the postsynaptic neuron. So thousands of different dendritic regions within the postsynaptic neuron are going to be depolarizing when this presynaptic neuron releases excitatory neurotransmitters. This is something that is going to become important to realize as we continue on with our discussion of the action potential. So let's focus back in on this one synapse. What has happened is, thanks to the excitatory neurotransmitters, these ligand-gated channels have opened up and allowed sodium to come in to this dendritic region of the postsynaptic neuron. The influx of sodium into this dendritic region depolarized this dendritic region, in my example, from -70 to -40 millivolts. Now, going back to the discussion we had a couple minutes ago, what you want to think about is the fact that this is just one portion of this one dendrite. Okay? This isn't the entire dendrite. Just this one portion of this one dendrite is what makes up the end or second half of the synapse. So there's a lot more dendrite that exists. And what we want to be thinking about is, yes, we've depolarized this one dendritic region from -70 to -40, but have we done anything to the other portions of the dendrite? And the answer is no. In these dendritic regions that lie next to or adjacent to the synapse, these dendritic regions inside haven't changed at all. They're still -70 millivolts. So what good is depolarizing this one singular dendritic region from -70 to -40? What's good about it is it's going to have an influence over that adjacently negative area. So as we have depolarized this one dendritic region from -70 to -40 millivolts, the adjacent dendritic regions or areas of the dendrite are still -70. Okay? So now this dendritic region that we have depolarized underneath the synapse, it is now more positive than the adjacent area of the dendrite where it is more negative at -70. And what we know is that areas of positivity like to flow towards areas of negativity and vice versa. So what that really means is this dendritic region, which has depolarized, become more positive, is going to want to flow towards this adjacently negative area because that area is more negative than it is. And it's also actually true that this area of negativity within the dendrite is going to want to flow towards this dendritic region, which is more positive. But for the sake of keeping things a little bit more simple, we are just going to talk about this as if the area of positivity is flowing towards the area of negativity. So what happens? If this slightly depolarized region of the dendrite begins to move towards this adjacently negative area, it is going to actually, of course, depolarize that adjacently negative area, right? Because sodium ions are going to flow from the depolarized dendritic region into the adjacently negative dendritic region, and that adjacently negative dendritic region is going to gain positively charged sodium ions, so thus it is going to depolarize too. It is going to become more positive. Now the interesting thing is, this adjacent area, right, where it's negative 70 presently, is not actually going to be able to be depolarized all the way to negative 40 like the area underneath the synapse was. Yes, it's going to become more positive as this as the sodium ions, as this depolarization, which is really a small wave of electricity, moves from this dendritic region under the synapse into this adjacently negative area. But it's not going to depolarize by a full positive 30 millivolts. Let's say it only depolarizes by 29 millivolts. So it is only going to make it to negative 41. The same exact thing is going to happen as it continues to move into these adjacently negative areas. Because now what have we done? We've made this adjacent region of the axon go from negative 70 to negative 41, thanks to the fact that the sodium ions, the depolarization wave of positivity, moved into the adjacent area where it was more negative. And it depolarized that area by 29 millivolts. But now this adjacent area is negative 41, and the area that is adjacent to it within the dendrite is still negative 70. Right? So now this area of the dendrite is much more positive than this area of the dendrite. So it's going to continue to flow into the adjacent region. And you can imagine the exact same thing is going to happen. It's going to depolarize this adjacent region. But let's say it's not going to be able to depolarize it by a full 29 millivolts. Maybe it can only depolarize it by 28 or 27. Right? It only gets up to negative 43. The same thing is going to keep happening as this small electrical wave, this depolarization, continues to travel down the dendrite. As the wave of positivity moves into these adjacently negative areas, it's going to continuously fall apart. The more accurate way of saying this is the signal is going to decrement as it moves from the initial area in which it was created, in this case underneath the synapse, away from the site of origin, away from the site that it was originated. It falls apart. It decrements. Discussing why the signal decrements would be too much of a deviation from the topic of this lecture, but if you're interested, that topic is covered when discussing how myelin sheath work to increase the conduction velocity of action potentials. What would be occurring right now is this depolarization, this small electrical impulse, would be moving from the dendritic region that it originated in. This dendritic region would be, of course, the dendritic region that lies right underneath the axon terminal button of the presynaptic neuron. This dendritic region was driven to negative 40 millivolts, right? It depolarized from negative 70 to negative 40, got 30 millivolts more positive, and it would be moving towards the subsequently negative areas within the dendrite, right? Where the dendritic regions are still negative 70 millivolts. And as it moves into those regions, it would drive those regions up, right? It would depolarize the interior of those regions. And in the example I gave, it drove the next dendritic region from negative 70 to negative 41, and then it drove the next dendritic region from negative 70 to negative 43. Right? So what's happening is as the signal, the electrical impulse, moves away from the point of origin, it's decrementing. It's falling apart. What that's technically called in physiology is a graded potential. Any depolarization, electrical impulse that decrements as it moves away from the point of origin is technically referred to as a graded potential. That's exactly what we're seeing here. And a big question is, where ultimately is this graded potential going to go? Well, of course, it's going to keep moving towards the areas which are more negative. That logically would be into the cell body. Right? So as this graded potential moves into the cell body, as this wave of positivity, this electrical impulse moves into the cell body, it's going, of course, to depolarize the cell body. But it's not going to depolarize the cell body by the same degree to which the last region was depolarized, right? So what I'm saying by that is, if we got this dendritic region right before the cell body to depolarize from negative 70 to negative 43, as it moves towards the next negative area, which would be into the cell body, it's not going to depolarize the cell body from negative 70 to negative 43. Right? It may only be able to depolarize the cell body from negative 70 to negative 50, for example. It was only able to depolarize the cell body by 20 millivolts. The cell body is where these graded potentials really has a tendency to fall apart for a variety of reasons that we can't get into in this specific lecture, but the volume of space certainly has an influence over how much that particular area can be depolarized. Anyways, where is this now wave of positivity going to head towards next? And the answer is, well, we know that within the axon hillock, within the initial segment, all throughout the axon, it's still negative 70. So logic, I think, would tell us that this depolarization, this graded potential, is going to move towards the next negative area, which would be essentially towards the axon hillock. And now let me go backwards for just a second and say, what would be occurring right now would not just be one of these graded potentials. If you remember, between a pre- and postsynaptic neuron, in reality, there would be thousands of synapses. And when that presynaptic neuron generates an action potential, it's going to release neurotransmitters from all of its axon terminal buttons. And those neurotransmitters, since we're talking about excitatory neurotransmitters, are going to open up ligand-gated channels on thousands of different regions of these different dendrites. What I'm saying is there would be synapses that exist between presynaptic axon terminal buttons and postsynaptic dendrites in thousands of different locations. And since the presynaptic axon terminal buttons are all releasing excitatory neurotransmitters, that means those excitatory neurotransmitters are going to bind to ligand-gated channels on all of these thousands of different dendritic regions. Or we could say dendritic plasma membranes, because that's where the ligand-gated channels are embedded. And that's going to allow for what? Sodium, well, let me erase this a little bit. that's going to allow for sodium to come in to all of these different regions and depolarize all of those different dendritic regions internally, right? And where are those depolarizations, which, as I think we've discussed now, are really graded potentials? Where are those depolarizations, graded potentials, going to head? They're all going to follow the same path, right? They're all going to move towards areas that are subsequently negative, which really means down the dendrites into the cell body towards the axon hillock. What I did with this one specific graded potential that I was showing you was certainly an exaggeration. One singular graded potential is not going to be able to depolarize a dendritic region by that much. But I said it for the purpose of making a point. The principle is the same. That dendritic region will become depolarized thanks to the excitatory neurotransmitters binding to ligand-gated channels on the dendrites and allowing for sodium to come in. And as that depolarization moves away from the point of origin, it will fall apart, as we have shown. It just wouldn't be quite as dramatic as I displayed. And the reason it doesn't have to be as big of a depolarization or as dramatic as I have shown you is because these graded potentials would be coming from thousands of different dendritic regions within the neuron. And since these graded potentials would be coming from thousands of different locations within thousands of different dendrites towards the cell body, it is certainly feasible that enough sodium would move from these dendritic regions into the cell body to drive it up to negative 50 millivolts. Now, there's a whole separate lecture and discussion about how many neurotransmitters and how frequently would neurotransmitters have to be released by the presynaptic axon terminal buttons in order to actually allow enough sodium in to accomplish this. And that discussion deals with concepts that are referred to as spatial and temporal summation. But that is a little bit outside of the topic of this lecture and better saved for a different video. All I have tried to accomplish with you here is to get you to see that all of these different depolarizations, graded potentials, are going to move from the dendritic regions towards subsequently negative areas. And that means they're all going to flow towards the cell body and ultimately, what we're going to talk about next, towards the axon hillock. So what I'm going to do with you now is try and show you what happens at the axon hillock. So in here would be generally the region of the axon hillock. Comes right before the axon. It's kind of where the axon is beginning to form. It is what actually connects the cell body to the axon. And inside, internally, within the axon hillock, within this region, internally, the resting membrane potential would still be negative 70 millivolts. But what's headed towards the axon hillock? The answer is depolarizations, graded potentials from many different regions of the neuron, specifically the neuron's dendrites. So again, we said the interior would be negative 50 millivolts within the cell body, and within the axon hillock, the interior is negative 70. And clearly, the inside of the cell body, right next to the axon hillock, inside of the cell body, it is 20 millivolts more positive, negative 50, than the axon hillock, where it is negative 70. So the membrane potential inside of the cell body is more positive than inside of the helic region. So these graded potentials, right, they're going to move towards, ultimately, the axon helic. And what that really means is a wave of positivity, mostly sodium ions, are going to begin to flow into the helic region. And I think at this point you probably know the answer. What's going to happen to the helic region? The helic region is going to become more positive. It is going to depolarize. And the objective here, if we want an action potential to occur, is we need to get the helic region to something called threshold. We need to get the helic region from negative 70 millivolts up to negative 55 millivolts. Another way of saying this is we need to depolarize the axon helic by 15 millivolts, get it from negative 70 to negative 55 in order to get the helic to threshold so that an action potential can occur. So the objective, if there is such a thing, of all of these different graded potentials coming from all of these dendritic regions is to move towards the axon helic where it is more negative and try to get enough sodium into the axon helic region to depolarize it by 15 millivolts. And if that can happen, then threshold will be hit within the helic and an action potential will occur. So how will this action potential occur just because we depolarize the helic region by 15 millivolts? To understand how an action potential will be generated within the axon helic when it gets to threshold, the first thing that you have to do is recognize within the plasma membrane of the helic region, there is a very high density of what are called voltage-gated sodium channels. So these are truly sodium channels. They are a channel that will allow sodium to travel through them. But they're voltage-gated. What this really means, at the moment, if the interior of the helic is negative 70 millivolts, then these voltage-gated sodium channels are closed. They're not allowing any sodium to come or go. But if we can get the helic region from negative 70 to negative 55 millivolts, right? We can depolarize it by 15 millivolts, and we can get it to threshold. What will happen is these voltage-gated sodium channels will open. They have a gate on them, and that gate is voltage gated. What that means is the interior voltage of the helic has to change, right? It has to actually depolarize, become 15 millivolts more positive in order for those gates to open up. And that's exactly what we've done here, right? We've gotten these graded potentials that have moved from the dendritic regions, which are really mostly made up of sodium ions, right, from the dendritic regions into the cell body towards the helic where it's more negative all along the way. And we've gotten these graded potentials, enough sodium ions into the helic region to depolarize it by 15 millivolts. And that then triggers these voltage-gated sodium channels within the axon helic to open up. The voltage is what does it, or the voltage change, I should say. So, even if these voltage-gated sodium channels all open up, what does that actually mean? It means that the helic region has all of a sudden become much, much, much more permeable to sodium. Right? All of these voltage-gated sodium channels open. And now, all of a sudden, sodium has a lot of doors that it can travel through. And what do we know about sodium? Sodium is very high in the interstitial fluid, and it's very low in the intracellular fluid, the cytosol. So sodium has a strong chemical driving force to enter. What do we also know presently? Well, the interior is negative 55 millivolts. That's a very strong electrical driving force for sodium to want to come in. Sodium really wants to come into the hillock and all other regions of the neuron for that matter, but it can't because it doesn't have many leak channels that it can travel through. But now all of a sudden, within the axon hillock, lots of voltage-gated sodium channels open up. And now all of a sudden, sodium has many channels that it can travel through. And of course, it's going to come in. It's going to follow both its chemical and its electrical driving force, and it is going to shoot into the axon hillock region. And it is in fact going to depolarize this axon hillock region all the way to positive 30 millivolts. Why it stops at positive 30 millivolts will be discussed in the next lecture video. But for the moment, when threshold is hit within the hillock, lots of voltage-gated sodium channels open up. Sodium moves from the interstitial fluid through the voltage-gated sodium channels into the interior of the hillock region, and enough sodium is gained on the interior to drive the interior up from negative 55 all the way to positive 30 millivolts. What's been generated now is what will be and is presently an action potential. What I mean by will be is that the action potential by no means is over just yet. And why would that be the case? Because has anything changed throughout the axon? And the answer to that is no. Throughout all of the other axonal regions, it is still negative 70 millivolts. And don't let me confuse you. When I say throughout all of the other axonal regions, I am not saying the axon hillock is part of the axon, because technically it is not. So more appropriately said, throughout all of the axon, the interior is negative 70. And in the hillock, it's positive 30. So where do you think this very large wave of positivity, this electrical impulse within the hillock, is going to go? Well, it's going to move towards the next subsequently negative area, which is down the axon, where it is negative 70. So this action potential now, this big electrical impulse, is going to move from the hillock region into the axon, where it's negative 70 millivolts. And what that really means is a big collection of sodium ions is going to move from the hillock region into the first true axonal region. And those sodium ions, of course, are going to depolarize that region. But what effect is that really going to have? And to understand that, you have to realize that down the entire length of the axon plasma membrane, there are voltage-gated sodium channels. Voltage-gated sodium channels line the entire plasma membrane of the axon. So if the interior of the axon in these regions is negative 70, and this big electrical impulse, this action potential now, moves from the hillock region into the first axonal region, it's going to depolarize that region of the axon easily by 15 millivolts. Right? It's going to, with total ease, drive that region from negative 70 up to negative 55 millivolts, well past that actually. But what that's going to do, once that axon region gets from negative 70 to negative 55, once it depolarizes by 15 millivolts, what's going to happen is voltage-gated sodium channels within that region of the axon, within that region of the axon's plasma membrane, they're going to open up, right? They're closed at negative 70, and when the interior gets to negative 55, they're going to open. And what's going to happen is sodium is going to follow both its chemical and electrical driving forces, and it's going to enter into the interior of the axon, right? Sodium is going to move from the interstitial fluid into the intracellular fluid of the axon, and it's going to depolarize the interior of the axon all the way up to positive 30 millivolts. But what about the next region of the axon? The next region of the axon is still negative 70, and now this axonal region that we're discussing, the interior membrane potential is positive 30 millivolts, but the axon region that lies just next to it, the subsequent area, it's negative 70. So the same thing is going to happen. This now action potential, we'll discuss exactly what the term action potential means in just a moment, but this action potential is now going to move from this axonal region into the next. And the reason it's doing that is because it's moving from an area of positivity towards an area of negativity, and it's very easily going to depolarize this axon region from negative 70 to negative 55 millivolts. It would do much more than that even on its own. And what will that cause? Well, it'll cause voltage-gated sodium channels within this region to open up. And then sodium will move from the interstitial fluid down its chemical and its electrical driving force and drive this region from negative 55 all the way up to positive 30 millivolts. And I won't repeat the whole thing again, but I assume that you may know what's coming next, right? This action potential, this big electrical impulse, is going to move from this axonal region into this subsequent axonal region, and it's doing that because it's moving from an area of positivity to negativity, right? It's moving down the axon essentially right now, and what that's going to do is it's going to depolarize the subsequent region of the axon easily by 15 millivolts. Voltage-gated sodium channels are going to open up. Sodium is going to shoot in. Voltage-gated sodium channels are opening up. I mean, sodium is going to shoot in, drive the interior up to positive 30 millivolts, and then the same exact process is going to keep repeating, right? This is going to happen down the entire length of the axon. So now I have the opportunity to show you an image that is in basically every physiology textbook that has a horrible tendency to confuse lots of people. So what is being depicted here is in every one of these, that's the axon. Okay? And if you look closely, just pretend that this is the hillock region for the moment. We're just making that up. But on the interior, you can see what these are is negative, 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 negative. What that really means, if we're relating this to what I was discussing, the interior is negative 70 millivolts all throughout the axon. Great. What's happened inside of the hillock region, if that's what that is? The hillock region has become positive, 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 positive inside. What that really means is the hillock region would have gotten to threshold and went from negative 70 to negative 55 millivolts. Voltage-gated sodium channels opened up, and some sodium shot in, and that made the whole region positive, right? It drove the interior up to positive 30 millivolts. But then what happens next is this action potential now, this electrical impulse, this positivity, right, it moves into the next subsequently negative area, which is the adjacent part of the axon. And it easily depolarizes that region of the axon to threshold, up by 15 millivolts to negative 55. And as that region of the axon depolarizes to negative 55 and threshold is hit, we know that more voltage-gated sodium channels in the plasma membrane open up. And that causes sodium to shoot in and drive the interior up to positive 30 millivolts. And that's what's being depicted at the bottom here. What these types of images are trying to show you is what's called propagation of the action potential. Propagation of the action potential just means how the action potential moves down the axon. That's what these images are depicting, although they can be quite confusing. And for whatever reason, they all tend to look the same, which means they're all almost equally confusing. So just check it out, right? I realize that now this is saying this region is repolarizing. We'll get to that in another video, in the next video, actually. But what's important to see is how in the first image, this region, this hillock region, or a region of the axon, it doesn't matter. That region, it was depolarizing at first, right? The interior depolarized to positive 30. And then what happens is the next region depolarizes. Well, how could that be? Well, the next region depolarizes because the action potential, that electrical impulse, moves from that first region into the next region of the axon, right, where it's still, to start off with, negative 70. And as it gets that region of the axon to threshold, drives it up to negative 55 millivolts, voltage-gated sodium channels open up, sodium shoots in, and that depolarizes that region, right? It depolarizes it to positive 30, because you'll notice, if we look at the image on the top, it's negative, 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 negative everywhere. And now, on the image underneath it, where it now says that region is depolarized, it's positive, 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 positive everywhere. And the reason for that is, of course, sodium has come in and it has depolarized it, made it more positive all the way to positive 30 millivolts. And now you'll notice on the image on the bottom, what's happening is the next region is going to become depolarized. If we look at the adjacent region in the image in the middle, it's still negative, negative, negative everywhere, right? That would be because the inside is negative 70. And then what's going to happen is the action potential is going to move from the depolarized region into the next region of the axon, where it's still negative, right? Negative 70. And as that happens, as that area of positivity moves towards that area of negativity, it's going to easily depolarize this region where it's negative to negative 55 millivolts. Voltage-gated sodium channels are all going to open up. Sodium is going to shoot in and is going to drive the interior up to positive 30. And now this region, if you look at the bottom, will of course be depolarized because of that. It'll all be positive. So that's what these types of images show you. They show you how the action potential propagates along the axon. I would just argue that they kind of do a bad job of it. You can see the action potential, right, propagating down the axon. So as long as we're on the topic, what is an action potential? An action potential, by definition, is a non-decremental electrical impulse. It's the opposite of a graded potential, in the sense that as an electrical impulse moves from a dendritic region towards the cell body and towards the hillock, it falls apart, it decrements. But an action potential doesn't. If you follow the action potential down the axon, every region will be positive 30, positive 30, positive 30, positive 30. It's always the same. The degree to which the interior becomes depolarized is always the same. It doesn't decrement. That is the definition of an action potential. Graded potentials decrement, action potentials don't. So the point is, and that's why you hear it this way, when you get the hillock to threshold, an action potential will be generated. What that essentially means is a non-decremental wave of electricity is about to travel down the axon, which we call an action potential. So let's depict what that would actually look like in this image. First of all, we get the hillock region to threshold thanks to those graded potentials coming from the dendritic regions. We get the hillock region to threshold, negative 55 millivolts. Voltage-gated sodium channels within the plasma membrane of the hillock region will open up. Sodium will shoot in, drive the interior up to positive 30 millivolts. All throughout the axon, it would still be negative 70 millivolts. So what's going to happen is now the action potential is going to begin to move, or propagate as it's called, down the axon. Within the hillock region, it's positive 30 millivolts. In the adjacent region of the axon, it is negative 70 millivolts. So the action potential will move to an area where it is more negative, and to polarize that region, voltage-gated sodium channels will open up, and that will make that region positive 30. And rather than go through the whole thing again, the action potential, as it moves down the axon, will ultimately allow for sodium, thanks to the opening of voltage-gated sodium channels, to come in to all of these different regions of the axon and depolarize all of them to positive 30 millivolts. And now what's important to recognize is the axon terminals are part or are extensions of the axon, right? So if the action potential is traveling down the axon, you better believe it's going to travel into all of the axon terminals as well. So those axon terminals must have voltage-gated sodium channels within their plasma membranes, and they do, and that's going to make these axon terminals, the interior of them, right, they're going to become positive 30 millivolts. But what's the point of all of this? So this is an action potential, a non-decremental wave of electricity that travels down the axon into the axon terminals. The purpose of the action potential within a neuron, as I have already told you, even though I haven't gone into the detail of it, it's to cause the release of neurotransmitters. Right? The action potential is what's going to cause exocytosis of neurotransmitters from the axon terminal buttons. That's the point of the action potential. So how exactly does the action potential do this? So let's draw an axon terminal and axon terminal button. Inside of the button, there are vesicles filled, usually with neurotransmitters. What exists in the plasma membrane of the button are voltage-gated sodium channels. Inside of the button right now, we will say it is negative 70. But what's going to be traveling into the button? Well, an action potential is, right, coming from a different portion or different region of the axon terminal. And it's going to move into the subsequently negative area of the axon terminal, which we have depicted. And that means that this area is going to become depolarized easily to negative 55 millivolts. And that's going to cause these voltage-gated sodium channels to open up. Sodium is going to shoot in through its chemical and electrical driving force and drive the interior up to positive 30. And now where does it go? Well, inside of the button, the resting membrane potential is negative 70 millivolts. So, well, that clearly means that the action potential is going to want to travel into the button, and it does. And when the action potential moves from the axon terminal into the button, from an area of positivity towards an area of negativity, it's going to depolarize the interior of the button. And now, in the plasma membrane of the button, there are voltage-gated channels, but they're not voltage-gated sodium channels. They are voltage-gated calcium channels, but they behave just like voltage-gated sodium channels. If the interior of the button is depolarized by 15 millivolts, then the voltage-gated calcium channels are going to open up. And what do we know about calcium? Calcium is a positive ion that is high in the interstitial fluid, and it is low in the intracellular fluid, in the cytosol. So it has a chemical driving force to enter into the neuron, specifically into the button. But what does it also have? At the moment, the interior of the button would be negative 55 millivolts. And that means that calcium also has an electrical driving force to come in. So the point is, if you can depolarize the button by 15 millivolts and open up the voltage-gated calcium channels, now calcium is going to have a path to come into the button, which it wants to do anyways. Right? It's going to follow its chemical and its electrical driving force, and it is going to shoot into the button. And the influx of calcium, we know, triggers these vesicles to move towards the distal end of the button, right? Towards the plasma membrane of the distal end of the button, and dock to the distal end of the button on the plasma membrane using these things called snares. And when these vesicles dock to the plasma membrane at the distal end of the button, the vesicles open up and they allow for these neurotransmitters to leave the button, which is known collectively as a process as exocytosis. This influx of calcium causes exocytosis of neurotransmitters. And this is what the action potential accomplishes. The action potential, this non-decremental wave of electricity, serves the purpose of moving into the buttons and causing the buttons to depolarize and become more positive. And then that action potential, by depolarizing the buttons, opens voltage-gated calcium channels. That allows calcium into the buttons, which then triggers exocytosis of neurotransmitters. The calcium tells the vesicles to move to the button plasma membrane and release their neurotransmitters into the interstitial fluid. And now, of course, the question is, what do the neurotransmitters do? So let's pretend now that this is actually neuron number 2, and this is a neuron we haven't seen before, which is neuron number 3. Neuron number 2, which was the postsynaptic neuron, now becomes the presynaptic neuron, which is, I like to number the neurons rather than talk in pre and postsynaptic terms, because as you follow, the neurons like dominoes, they all switch between being post and then presynaptic neurons. But neuron number 2, which is the one that we were looking at that was generating an action potential. It generates an action potential. That action potential then causes exocytosis of its neurotransmitters from its axon terminal buttons. Those neurotransmitters are now going to be floating around within the synaptic cleft, which is going to be the space that exists between the axon terminal buttons and usually the dendrites of another neuron, what would be called the postsynaptic neuron, in our case, neuron number 3. So we can probably imagine that on the dendrites of neuron number 3, specifically the portion of the dendrites that lie underneath the axon terminal buttons, there are going to be ligand-gated channels. And let's pretend that those ligand-gated channels bind a specific excitatory neurotransmitter, which was just released by neuron number 2. If that's the case, and this is neuron number 3, and this is neuron number 2, then these ligand-gated channels are going to have this specific excitatory neurotransmitter that neuron number 2 just released. These ligand-gated channels are going to have that neurotransmitter bind to them, and that's going to cause them to open up. And what are they actually? Well, if they bind excitatory neurotransmitters, these receptors, these ligand-gated channels, then they are non-specific or non-selective cation channels. And the same exact process is going to repeat. Right? Inside of the dendritic region of neuron number 3, it is negative 70 millivolts. And now this excitatory neurotransmitter released by neuron number 2, the presynaptic neuron now, is going to increase the sodium permeability of neuron number 3 by opening up these ligand-gated channels. And sodium is going to have a passageway. It's going to follow its chemical and its electrical driving force into neuron number 3, and it's going to depolarize this dendritic region of neuron number 3, maybe to negative 40 millivolts by positive 30 millivolts. And then what's going to happen? Well, these dendritic regions, which are part of neuron number 3, right, are going to become depolarized. And these depolarizations, these waves of positivity, which as you know now are really graded potentials, they're all going to head into the subsequently negative areas of the dendrites, towards the cell body, towards the hillock. And the objective of these graded potentials is to try and depolarize the hillock to threshold. If you can get enough sodium into the hillock of neuron number 3, then neuron number 3 will hit threshold. And if it hits threshold, then neuron number 3 will generate an action potential, right? A non-decremental wave of electricity. In the case of a neuron, the action potential is going to travel down the axon. In the case of other cells, the action potential is always going to travel down a plasma membrane, but it may not travel down an axon, for example. So the action potential is going to travel down the axon into the axon terminals, and that then is going to cause neuron number 3 to release neurotransmitters from its axon terminal buttons, thanks to the action potential causing voltage-gated calcium channels to open up in the axon terminal buttons of neuron number 3, which triggers the influx of calcium into those buttons and thus the exocytosis of neurotransmitters. And what you'll really end up with here is a domino effect. Typically, to accomplish some brain process, it is going to require the passing of action potentials between hundreds or thousands of neurons. One neuron is going to generate an action potential, pass the action potential to the next neuron, pass it to the next neuron, and the next, and the next, and the next, and the next. And what we've gone through in this lecture is we've looked at how a neuron generates an action potential, how it propagates an action potential down its axon, and then how it passes an action potential. And it does that thanks to the release or through the release of neurotransmitters. In the case of passing an action potential, that's going to be excitatory neurotransmitters. So let's finish this video by taking a look and looking at the first half of a graph that tends to baffle the minds of many people, myself included, for many years. Whenever you hear about action potentials, this thing always shows up. And it is incredibly confusing unless you truly know what you're looking at. And then it's actually not that confusing. So what this is showing, first of all, you have to realize what this would be showing. It would be showing the membrane potential, but specifically, it would need to be within the hillock. It could also technically be in a different part of the axon, but I always tell people to imagine this as if it is the membrane potential of the hillock. The resting membrane potential of the hillock is what? It is negative 70 millivolts. Well, we start off at negative 70 millivolts. All right, well, what if graded potentials start moving from the dendritic regions towards the hillock region? Well, those graded potentials involve sodium moving into the hillock region. And what will happen is the hillock region will begin to become depolarized, right? It will move from negative 70 and it'll begin to become more positive. And if you can depolarize the hillock region from negative 70 millivolts to negative 55 millivolts, what happens? Well, you hit threshold. So what is being depicted here in the image is, I like to say, inside of the hillock, the image is showing the hillock hitting threshold, negative 55 millivolts. And if the hillock hits threshold, we know what happens. Voltage-gated sodium channels open up. And then sodium shoots in and drives the interior from negative 55 millivolts to positive 30 millivolts. And look at that. That is exactly what happens. So that is all the first half of this graph is showing. Now you could relate this to any other part of the axon. Like we could look at the membrane potential within the adjacent part of the axon and it would be negative 70 millivolts. So this could be looking at that adjacent region of the axon. And if this action potential moves into that region, it's going to do the exact same thing, right? It's going to depolarize that region from -70 up to -55 millivolts. That region is going to hit threshold. Voltage-gated sodium channels are going to open up. Sodium is going to shoot in. It's going to drive the interior from -55 millivolts to +30 millivolts. And then the action potential is going to move on to the next region of the axon. So technically, this can be showing any region of the axon, but as I said, I like to think about it really as being the hillock because that's the most relevant. Clearly, what is missing is the whole second part. Why, for example, does the interior get stuck at +30? Why does it get stuck at +30? And then, why does the interior go back down to -70, and it actually goes beyond -70 millivolts? This whole process of bringing the interior from +30 back down close and beyond the resting membrane potential and then back up to the resting membrane potential, that whole process is called repolarization. Basically, when you get one of these regions of the axon or the axon hillock to +30, you need to bring it back to -70. And the reason for that is so that another action potential can happen, because some neurons can literally generate thousands of action potentials per second. And in order to do that, the interior must repolarize back to a negative value, like -70, the resting membrane potential. Otherwise, of course, another action potential can't happen. So in part 2, which you can find here, what we are going to take a look at is how the neuron repolarizes. How does every region go from +30 back to -70? And repolarization is a very confusing concept as well. But if it is discussed in the right way, which I will try to do in the next video, I tend to find it pretty manageable.